Hello all, welcome to this course on Elements of Mechanical Engineering. My name is D. A. Ramacharyalu and I am working as an assistant professor in the Department of Mechanical Engineering. We are in the first module of the course Elements of Mechanical Engineering, where we are studying the basics of thermodynamics. In the previous lectures, we have seen the different thermodynamic properties, different thermodynamic systems, and how a thermodynamic system state will change from one form to another form, and how the thermodynamic laws will affect the system. There are 4 laws: zeroth law, first, second, third law. So we have seen what are the limitations, applications of these laws, and where these laws are generally based on entropy, temperature, and enthalpy. So in this lecture, we are going to see some numericals on first law of thermodynamics. So in this slide, we can see the question. We are going to calculate the internal energy in this problem. Okay. Now, we'll see what is the question given. A system is subjected to heat transfer of 40 joules to a system, while the system does 10 joules of work. Later, there is a heat transfer of 25 joules out of the system, while 4 joules of the work is done on the system. What is the net change in the internal energy of the system? So this is a very simple problem where we are going to calculate the internal energy of the problem. The internal energy will be calculated by using the different formulas. We'll see. So first of all, we'll see what is the given data. Here in this question, heat transfer is given. Heat transfer to the system is 40 joules. So this is 40 joules. This is given to the system. And then 10 joules of work is done by the system. 10 joules of work is done by the system. So this is in the first case. 40 joules of heat is supplied and 10 joules of work is done by the system. This is first case. And second case is 25 joules of heat is transferred from the system. 25 joules is transferred out of the system. So it is taken out of the system. And 4 joules of work is done on the system. And some work is also done on the system. That is 4 joules. So using this data, we have to calculate what is the change in internal energy. We have to calculate change in internal energy, that is capital U. We have to calculate the value of internal energy. Now we'll go to the next slide. What is the basic strategy we have to follow in order to solve this problem? Okay. Now we'll see here in this problem, the first net heat transfer and net work done are to be calculated. Okay. We have 2 types of quantities which are being discussed in this problem. One is heat supplied and second one is work done. So these 2 quantities have to be selected, have to be calculated in such a manner so that we can go forward into the problem. Now, from the first law of thermodynamics, we have this equation. We know first law of thermodynamics is the one which deals with law of conservation of energy. So in law of conservation of energy, the simple principle is the energy is neither be created nor be destroyed, but it is converted from one form to another form. Okay. Now, from the first law of thermodynamics, we have this formula. Delta U is equal to Q minus W. Here, delta U is nothing but the change in internal energy, which is equal to the energy supplied to the system minus work done on the system or by the system. So this is the basic definition that is derived from the first law of thermodynamics. This formula is used for calculating the change in internal energy. Now in the picture we can see this is all the given data that is represented in the picture, where in the first case the energy given into the system is 40 joules. So that is taken as positive energy given to the system. And work done to the system, work done on the system is taken as negative. See here, this is positive and this is negative. Okay, we have two parameters in this problem. First one is Q, second one is W. There are two cases in which the first case, the energy is being supplied into the body or system and work is done on the system. So when some kind of energy is given to the system, it will take some work. So the work is taken as negative sign because we are doing work on the system. And in the second case, we have in reverse. This is energy that is taken out of the system. So it is taken as negative sign. And coming to work, work is done by the system. Here the system itself is doing some work. That means if we take the example of a IC engine, it will do some work when some energy is given to it in the form of fuel. It will do some work. The work is taken out of the system. Okay. Now see here. Here Q in is equal to 40 joules. Q out is equal to minus 25 joules. And again, work in and work out are minus 4 joules and 10 joules. Now, first thing we have to do is we have to calculate the net heat transfer and net work done. So simply we can calculate the net heat. So here the net heat transfer can be calculated by using this formula. Okay. So in this picture we can see this is 40 joules and this is minus 25 joules. So similarly we have done the same thing. We have calculated the net heat transfer to the system by using this equation, that is 40 joules, which is Q in minus Q out. Okay. The negative sign itself indicates the energy is being removed from the system. Now we got 15 joules of energy. So this is the amount of energy that is required, that is given to the system. Okay. So this is the net heat or net heat transfer done to the system. Similarly, we can calculate the total work. Total work can be calculated by, see in this picture, work given to the system and work done by the system. The values are there, minus 4 joules and 10 joules. Now we are going to calculate W, which indicates work done, the net work done, that is equal to 10 joules minus 4 joules, which is equal to 6 joules. Okay, we have calculated the value as 6 joules. Now we have to remember these two values. Here Q is equal to 15 joules and W is equal to 6 joules. Now we have to remember these values in order to calculate the internal energy change. Okay, now up to here it is clear. Now we can see in this slide the change in internal energy formula. So this is the formula for change in internal energy. So where delta U represents the change in internal energy and Q stands for change in heat transfer and W is the work done transfer. I mean net work done. So we have calculated the values of Q and W in the previous slide, where Q value is 15 joules and W value is 6 joules. So by using the formula that is derived from the first law of thermodynamics, we can simply say the net work done, the change in internal energy is equal to 15 minus 6 joules, which gives us 9 joules. Here we can also find by another method. Now what we have done is we have separately calculated the values of the work and heat. Okay. And we have calculated the change in internal energy, that is 9 joules. Now we will use a separate method for calculating the change of internal energy. Okay. Now why we are seeing another method we will discuss later. So from here we can also find the change in internal energy for each of the two steps. Okay. First, consider 40 joules of heat transfer. Okay. We are doing the same problem in a different method. Okay. So in first case, we have 40 joules of heat transfer to the system and 10 joules of work is taken out of the system. Okay. Now 40 joules is done, 40 joules of heat is transferred and 10 joules of work is taken out of the system. Now by using the same equation, here this is the same equation as derived from the first law of thermodynamics, change in internal energy. This is the same formula as this one. Okay. Now what we are doing is, we are calculating the change in internal energy separately for first step and second step. Okay. Here, delta U1 is equal to Q1 minus W1. Okay. And we can simply, from the given data, we can write Q1 is equal to 40 joules and W1 is equal to 10 joules, out of which we got 30 joules of energy. So this is the change in internal energy for the first case, where 40 joules of heat is transferred and 10 joules of work is done by the system. So here the answer is 30 joules. Remember this answer. So here the values that are important is, first one, 9 joules. This is the internal energy of the overall system. Now here we have calculated the internal energy for first case. Now consider the second case. Here 25 joules of heat is transferred from the system and 4 joules of work is done on the system. Okay. In this case, we can calculate the change in internal energy as delta U2, which is equal to Q2 minus W2. That is 25 minus of minus 4 joules. Why we have kept minus here? This is the negative sign that is in the formula, but this is the negative sign that is obtained from the negative work done. That means work is taken into the system. Okay. So totally we got minus 21 joules of energy. Here both signs have negative. Okay. So ultimately we got the answer as minus 21 joules. So what we are going to do is, we have separately calculated the value of internal energy in these two cases, delta U1 and delta U2. Now if we make the sum of these two values, delta U1 plus delta U2. So this is the change in internal energy in each case. That means there are two cases where we have to calculate internal energy. So ultimately we will get, here 30 joules is there, delta U1, and second one is minus 21 joules. So ultimately we got 9 joules, which is same as the value that is calculated by using a single method. See, this 9 joules is there. This is same as this value. So both the values of change in internal energy is exactly the same. So from this we can infer that with the change in internal energy is same, even though it is calculated in a single method or it is calculated by dividing it into some parts. Okay. So see here, if I calculate the internal energy in a single step, we got 9 joules. Now in the second process I have done it by dividing into two parts. So here also I got 9 joules only. So which indicates the change in internal energy is same in any case, even though we calculate the value by using a single method or dividing it into number of parts. Okay. So this is the first example for today, and we are going to see another example problem. That is, this is also a very small example where we are going to calculate the change in internal energy. Okay. Now we'll see the question. What is the change in internal energy of a system when a total of 150 joules of heat transfer occurs out of the system? Okay. And 159 joules of work is done on the system. Okay. Here only two conditions are given. One is 150 joules of heat is taken out of the system. From the system, the heat is taken. So that is simply Q out. Q out. And 159 joules of work is done on the system. So this is W in. You can simply say 159 joules of work is done on the system. So we have to remember that whenever there is a heat removal from the system, we have to give negative sign. And whenever there is work done on the system, that is also given negative sign. So heat Q in and W in, that is work done on the system, and Q is the heat given to the system. So this is taken as positive and this is taken as negative. And again, Q out, amount of energy that is taken out of the system, this is negative, and W out, this is taken as positive. So like this, we have to remember for which process we have to give negative sign. So whenever we are giving Q in, W in, so in these two, Q is given positive and the work done into the system is taken as negative. And in the second step, Q out is taken as negative and work done by the system is taken as positive. So by using this sign convention, we can simply calculate the change in internal energy for the entire system. Here there are only two parameters. One is Q out, which is minus 150 joules. Why we have given minus sign? Because the energy is the energy is taken out of the system, Q out. So that is why minus sign is given. And again, W is the work done on the system. So W in is also taken as negative. So this is 159 joules. So by using the first law of thermodynamics formula, that is delta U is equal to Q minus W, we can calculate the value of this system is simply we can calculate like this using this formula. So this is Q and W. Here delta U is equal to Q minus W, which is equal to minus 150 minus of minus 159, which gives you 9 joules, which is same as the answer for the previous problem. So in the previous question, we have seen a similar condition where we have calculated the change in internal energy. Here we have done the same thing in a single step where we have got the same answer. The change in internal energy is 9 joules. Okay. Now from using this formula, we have calculated change in internal energy. So what are the implications or what are the conclusions that we got from these two questions? Note, the change in the system in both the questions is related to delta U, which is change in internal energy, and not to the individual Q or W. So here, whatever the change that is done on the system, whatever the state change that is being done on the system will directly depend on the internal energy, and it does not depend on either Q or W. Q is the heat transfer and W is the work done. So we can clearly conclude that the heat transfer and work done will not change or affect the change in internal energy. Okay, and this is first conclusion, and second one is the system ends up in the state in the same state in both questions. So we have seen two examples today. First example is where we have calculated the process separately, and in the second case we have calculated the process by using a different set of instructions. Okay, in both the questions the state is same. It is following the same state. Okay, so these are the conclusions that we got from the two questions. Now we are going to see another example. So this is the question where we'll try to understand the given question. Here 100 kilojoules of heat is supplied to a system at constant volume. So this is a problem which is based on the constant volume and adiabatic process, etc., constant pressure process, etc. So for this we have to draw a PV diagram based on which we can calculate the solution. See in the question, 100 kilojoules of heat is supplied to a system at constant volume. Okay, at constant volume, 100 kilojoules of energy is supplied, heat is supplied. And the second point is the system rejects 90 kilojoules of heat at constant pressure. At constant pressure, we got 90 kilojoules of heat, and 20 kilojoules of work is done. 20 kilojoules of work is done on the system at the same condition. At the same pressure, 20 kilojoules of work is also done. Now, the system is brought to original state by adiabatic process. The system is brought to its original state by adiabatic process. Now, we have to calculate two things. First one is the adiabatic work, this one, and the values of internal energy at all end states if initial value is 105 kilojoules. Okay, we have to calculate these two values by using the given data. So now we will go into the problem. First of all, we have to draw a diagram, PV diagram. In this, we will indicate different stages that are given in the question. Now, in the question we can see the first step is 100 kilojoules of heat is supplied to a system at constant volume. So, first one is constant volume process where 100 kilojoules of energy is supplied. And second one is the system rejects 90 kilojoules of heat at constant pressure and 20 kilojoules of work is done on it. So, here constant pressure process where 90 kilojoules of heat is supplied and 20 kilojoules of work is done on the system. Now, from this given data, we can draw a simple diagram like this. First one is constant volume cycle. So, for constant volume cycle, I have drawn a straight line. I have drawn a vertical line because the volume is constant between process 1 and 2. Here, what is happening? 100 kilojoules of energy or heat is supplied to the system. Okay. Now, that is why I have written here. So, this is point step 1 and 2. This is a path where I have supplied 100 kilojoules of energy at constant volume. So, this is a constant volume process, the straight line from here to here. And after the point 2, we have a constant pressure process where 90 kilojoules of energy is supplied. 90 kilojoules of energy is supplied and 20 kilojoules of work is done. So, this is Q in and W out. So, both are taken as negative signs. So, this is negative and this is also negative. So, that is why between line 2 and 3. So, 2 and 3 must be a constant pressure process because it is given in the question. So, it is a constant pressure process where I have to draw a horizontal line at a constant pressure value. Between 2 and 3, the pressure is constant. And also, there are two things happening here, Q and W. That is, some amount of heat is supplied to the system, that is 90 kilojoules, and 20 kilojoules of work is done on the system. That is also 20 kilojoules. Okay, both are taken negative signs because Q in and W out. Okay, so between the process 2 and 3, what we have done is, this is a constant pressure process. So, in the question it is given that the system is brought to its original state by adiabatic process. So, from this we can understand that the system is undergoing a cyclic process, which means the step 3 and 1 are connected by a adiabatic process. We know adiabatic process is a constant temperature process where we can draw this curve. Almost all adiabatic processes are like this only. They are in the form of a tangential curve. So, here adiabatic process. So, the process between 3 and 1 is a adiabatic process. Now, we are going to calculate the work done. So, here the work done W12. W12 indicates the work done in the process 1 and 2. Okay. So, this is process 1 and 2. Between 1 and 2, the work done on the system or by the system is 0. There is no work done here. Okay, so this is 0. And the Q value, Q1 to 2, the amount of heat supplied into the system or out of the system, we have to calculate that one. So in the question it is given that Q1 to 2 is equal to 100 kilojoules. The heat is supplied to the system, so it is taken as positive. So Q1 to 2 is equal to 100 kilojoules. So this is the given data from the question. And now the change in internal energy, delta U is equal to U2 minus U1, or else we can write this in the form Q1 to 2 minus W1 to 2. So Q1 to 2 is nothing but 100 and W1 to 2 is 0. So finally we got 100 kilojoules. So this is the change in internal energy between 1 and 2. So this is delta U between 1 and 2. So this is the value we got here. Okay. And again, now we got the value delta U. Now we will substitute this value in this equation. Delta U is equal to U2 minus U1. Here we know that U2 is equal to, from this equation we can write U2 is equal to delta U plus U1. Here delta U is nothing but 100. That is what we got this in this equation. 100 kilojoules is the value for delta U. And U1 is nothing but the value given in the question. Okay, see here, 105 kilojoules. This is the value of internal energy at all end states if initial value is 105. Okay, initial internal energy is given in the question, that is 105 kilojoules. So that is substituted here. U2 is equal to 100 plus 105. So finally we will get 205 kilojoules. So this is the value of the final internal energy. Because the initial internal energy is given in the question, by using the delta U, we have calculated the final internal energy, that is U2, which is equal to 205 kilojoules. Okay, so this is one step where we have used the given data for first state, that is from point 1 to 2. Okay, we have calculated the work done and the change in internal energy between 1 and 2. Okay, so because the question is given like this, we have to calculate the adiabatic work and also we have to calculate the values of internal energies at all end states. Okay, which means we have to calculate the internal energy at different points like 2, 3 and 1. Now we'll go to the next slide where we have to consider the process between 2 and 3. Here 2 and 3. Between the process 2 and 3, it is a constant pressure process. Okay, and constant pressure process, we have Q is equal to 90 kilojoules. Here negative sign is taken because Q is supplied, the energy is supplied to the system, and W is equal to minus 20 kilojoules. This is also negative because the energy work is done by the system. Okay, negative sign. Now using this formula, that is delta U is equal to, because we are studying the process between 2 and 3. So we have to write like U3 minus U2, which is equal to Q2 to 3. This is Q2 to 3 and this is also 2 to 3. So Q2 to 3 minus W2 to 3. So this value we have to calculate by substituting the values. This is minus 90 minus of minus 20. So finally we will get minus 70 kilojoules. Minus 70 kilojoules is the change in internal energy in the process 2 to 3. Okay, we have considered 2 to 3 process now. Now this minus 70 kilojoules is there. Now from this equation, delta U is equal to U3 minus U2. So in this process, the final internal energy will be taken as U3 because the process starts from 2 and ends at 3. So the internal energy at point 3 is equal to 105 kilojoules. That is taken, 205 kilojoules, that is taken from the previous cycle. Okay. Now here U3 is equal to, we can change this equation like U3 is equal to delta U plus U2. Okay. I have just rewritten this equation. U3 is equal to, now this is taken to the left side. Now U3 is equal to delta U is nothing but minus 70 kilojoules plus U2. U2 is the energy that is derived in the previous set of process, where we got U2 is equal to 205 kilojoules. Okay. Now we have to substitute this 205 kilojoules here. So this will give you the value 135 kilojoules. So this is U3. This is the value of U3. At point 3, we have calculated the internal energy. So final internal energy at this point is 135 kilojoules. The final energy at point 2 is 205 kilojoules. That is calculated in the previous slide. Now we will go to the last slide. So here we will consider the process 3 to 1, between 3 and 1. So it is given in the question that between point 3 and 1, it is an adiabatic process where there is no energy or there is no work done. Okay. Now we have to calculate this one by using, so between 3 and 1, the Q3 to 1 is equal to 0. There is no heat transfer, and delta Q is equal to, so we are calculating the entire change in heat transfer, that is equal to delta Q, that is 100 minus 90 is equal to 10 kilojoules. So this is taken from the given data, and delta W is equal to minus 20 plus W3 to 1. This is we have to calculate. We don't know this value yet. From this value we can calculate like W3 to 1 is equal to 20 plus delta W is nothing but 10 kilowatts. This is given in the question. Okay, 10 kilojoules. So W3 to 1 is equal to 30. So this value is equal to 30 kilojoules. So W3 to 1 is nothing but the adiabatic work. That is the work done during the process 3 to 1. Okay. Now W3 to 1 is nothing but 30 kilojoules. Okay. So we have calculated the given questions. We'll see what are the topics we have to calculate in this question. First one is adiabatic work, and second one is internal energies at all endpoints, end states, if the initial value is given. Now here the adiabatic work is nothing but W3 to 1. So the adiabatic work is nothing but the work done during the adiabatic process, that is 30 kilojoules, and energies, internal energies at different points, like U2 is equal to, U2 is nothing but 205 kilojoules. U2 is 205, and U3 is equal to 135 kilojoules. So this is the final answer we got here. U1 is already known, that is given in the question. Okay, U1, U2, U3, and work done in the process 3 to 1, that is adiabatic process. So by using the first law of thermodynamics, we have solved this entire problem. Okay, we have calculated adiabatic work and we have calculated internal energies. Okay, now in the next lecture we are going to see some more problems on other thermodynamic laws, that is second law, third law, and 0th law of thermodynamics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.